Right now, in another universe, you made a different choice. You took the job you turned down. You married someone else. You're living a completely different life. And in another universe, you don't exist at all. This isn't philosophy. It's physics. The mathematics of quantum mechanics suggests that every time a quantum event occurs, every time a particle could go left or right, decay or not decay, the universe splits. Both outcomes happen in separate, parallel realities, which means there are infinite versions of you, living infinite versions of your life right now in universes you'll never see. Welcome to the multiverse. And the evidence? It's more convincing than you think. The idea of parallel universes sounds like science fiction, but it emerges naturally from some of our best-tested theories in physics. It's not something scientists invented because it's cool. It's something they discovered because the math demands it. And once you see the evidence, you can't unsee it. The universe, or rather, the multiverse, is far stranger than anyone imagined. Let's start with the most famous version, the many worlds interpretation of quantum mechanics. Remember the double-slit experiment? When you're not observing, particles exist in superposition, multiple states at once. When you observe, the wave function collapses, and you see one outcome. But here's the question that haunted physicists for decades. What happens to the other possibilities? The Copenhagen interpretation says they just disappear. Poof, gone. But that's deeply unsatisfying. Information can't just vanish. So, in 1957, a young physicist named Hugh Everett proposed something radical. Nothing collapses. All possibilities happen. When a quantum measurement occurs, the universe splits. One branch where the particle went left, another where it went right. Both are equally real. You just can't access the other branch because you're entangled with one outcome. This is the many worlds interpretation. And it sounds insane, but it solves the measurement problem without introducing magical collapse or special roles for observers. It's deterministic, no randomness, just branching. And it's been gaining traction. Major physicists like David Deutsch, Sean Carroll, and Max Tegmark take it seriously. Why? Because it's the simplest explanation that fits the math. Every other interpretation adds extra assumptions. Many worlds just takes the Schrödinger equation seriously and follows it to its logical conclusion. But if many worlds is true, the implications are staggering. Every quantum event splits the universe. And there are trillions upon trillions of quantum events happening every second. In your brain alone, neurons are firing, chemicals are bonding, quantum processes are occurring constantly. Each one creates a branch, which means every second, countless versions of you diverge. In one universe, you sneezed. In another, you didn't. In another, a cosmic ray hit your brain and flipped a neuron, changing your thought mid-sentence. All of these universes exist. All of these versions of you are conscious, living their lives, completely unaware of each other. And it goes deeper. Not just your choices, but every possible outcome of every event in history happened somewhere. In some universe, the asteroid that killed the dinosaurs missed Earth. In another, Hitler won World War II. In another, humans never evolved. In another, a completely different form of intelligent life dominates the planet. Every possibility allowed by quantum mechanics has a universe where it happened. The number of parallel universes isn't just large, it's infinite. An infinity so vast, it's hard to even conceptualize. Now, you might ask, if we can never observe these other universes, is this even science, or is it just unfalsifiable speculation? That's a fair question, and it's one physicists struggle with. The problem is, many worlds makes the same predictions as other interpretations for any experiment we can currently do, so we can't directly test it. But there are indirect tests. For example, quantum computers. They perform calculations by exploiting superposition, existing in multiple states simultaneously. Some physicists argue that the computational power of quantum computers is evidence for many worlds. Where does the computation happen? If a quantum computer with a few hundred qubits can explore more possibilities than there are atoms in the observable universe, where is all that processing occurring? David Deutsch argues it's happening in parallel universes. The quantum computer is outsourcing its calculations to other branches of the multiverse. That's a testable claim. If quantum computers keep scaling up and performing tasks no single universe explanation can account for, that's evidence. Another test involves quantum interference. In many worlds, branches can interfere with each other under certain conditions, creating observable effects. Experiments with quantum erasers and delayed choice setups show interference patterns that are hard to explain without invoking multiple realities coexisting and interacting. The math works. The predictions match. The question is whether we're brave enough to accept what the math is telling us. But many worlds isn't the only type of multiverse. There's also the Level I Multiverse, infinite space. Here's the idea. If the universe is infinite in size and matter is distributed roughly uniformly, then every possible configuration of matter must occur somewhere. And if there are infinite instances, every configuration occurs infinitely many times. Which means somewhere out there, far beyond the observable universe, there's an exact copy of you. Same atoms in the same positions, living the same life. In fact, there are infinite copies, some exactly identical, some with tiny differences, maybe one atom out of place, some with major differences, you with a different job, different family, different history. This isn't wild speculation. It follows from basic probability and the cosmological principle, the idea that the universe is homogeneous on large scales. If the universe is infinite and matter is distributed uniformly, then all possible arrangements happen, including copies of Earth, copies of you, copies of this exact moment. The observable universe contains about 10 to the 80 atoms. The number of possible arrangements is huge but finite. If space is infinite, every arrangement repeats. Cosmologist Max Tegmark calculated that your nearest identical copy is about 10 to the 10 to the 29 meters away. That's a 1 followed by 10 to the 29 zeros meters, unimaginably far. But if the universe is infinite, it exists. Then there's the Level II Multiverse, eternal inflation. Our universe began with the Big Bang, but according to inflationary theory, the Big Bang wasn't a one-time event. Inflation, the rapid expansion of space, is eternal. It stops in some regions, creating bubble universes like ours. But in other regions, it continues forever, spawning infinite bubbles. Each bubble universe has its own laws of physics, its own constants, its own properties. In some, the strength of gravity is different. In others, the electromagnetic force is stronger or weaker. Most of these universes are sterile, unable to support life. But in an infinite multiverse, every possibility happens. And we find ourselves in one of the rare universes where the constants are fine-tuned for life, because we couldn't exist anywhere else. This is the anthropic principle. The fine-tuning is real. The cosmological constant, the energy density of empty space, has a value that's absurdly small but non-zero. If it were slightly larger, the universe would have expanded so fast that galaxies never formed. If it were zero or negative, the universe would have collapsed. The value we observe is tuned to 1 part in 10 to the 120. That's not just unlikely, it's incomprehensibly precise. Why? The multiverse offers an explanation. There are infinite universes with different values. We're in one where it's right, because only in those universes can observers exist to ask the question. Critics call this a cop-out. It doesn't predict anything. It just says, "We're lucky." But supporters argue it's the most natural explanation given eternal inflation. And eternal inflation is supported by observations of the cosmic microwave background. The patterns of temperature fluctuations match inflationary predictions. If inflation is real and inflation is eternal, then the multiverse is real. Then there's the Level III Multiverse, many worlds quantum branching, which we already discussed. And finally, the Level IV Multiverse, the mathematical universe hypothesis. This is physicist Max Tegmark's most radical idea. He argues that if a mathematical structure is consistent and well-defined, it exists, not as an abstraction, but as a physical reality. Our universe is one such structure. But there are infinite other mathematical structures, each corresponding to a different universe with different laws of physics. Not just different constants, but different rules entirely. Universes where time has 2 dimensions. Universes where space is 5-dimensional. Universes with fundamentally alien physics we can't even imagine. If Tegmark is right, every logically consistent universe exists, and we're just one instance among infinite mathematical possibilities. This sounds like pure philosophy, but Tegmark argues it's testable. If our universe is a mathematical structure, then we should be able to describe it completely with mathematics. And so far we can. Every law of physics is a mathematical equation. Every particle, every force, every interaction, it's all math. And the deeper we dig, the more mathematical the universe becomes. Physicists have discovered unreasonable effectiveness of mathematics in describing reality. Why? Tegmark's answer: because reality is mathematics, not described by mathematics, but made of mathematics. If he's right, the multiverse isn't just real, it's inevitable. Every possible universe exists because every possible mathematical structure exists. Now, let's talk about evidence. Can we actually prove the multiverse exists? The honest answer is, not yet. But there are tantalizing hints. One is the cosmic microwave background. If our universe is a bubble in a larger inflating space, and it collided with another bubble in the past, that collision would leave a mark, a circular pattern in the CMB. Some researchers claim they've found such patterns. Others say it's just noise. The debate continues. Another hint comes from dark flow, a mysterious large-scale motion of galaxy clusters in a particular direction, possibly caused by gravitational attraction from matter outside our observable universe. If confirmed, that would be evidence of a larger cosmos beyond what we can see. There's also the fine-tuning argument. The constants of nature are so precisely calibrated for life that it's either an extraordinary coincidence, evidence of design, or evidence of a multiverse. Most physicists prefer the multiverse explanation. It's naturalistic and emerges from existing theories. And there's the quantum computer argument. If quantum computers continue to demonstrate computational power that exceeds what single universe physics can explain, that's indirect evidence for many worlds. But the strongest evidence might be philosophical. The alternatives to the multiverse are worse. If you reject many worlds, you're stuck with wave function collapse, an ad hoc, unexplained mechanism. If you reject eternal inflation, you have to explain why inflation started and stopped at just the right moment, which requires fine-tuning. If you reject the anthropic principle in a multiverse context, you're left with the fine-tuning problem unsolved. The multiverse isn't just a fun idea, it's the most elegant solution to multiple deep problems in physics. Of course, there are critics. Some physicists hate the multiverse. They say it's not science because it's not falsifiable. If you can't test it, it's philosophy, not physics. But defenders argue that we test theories, not their consequences. Quantum mechanics is testable. General relativity is testable. Inflation is testable. If those theories lead to a multiverse, then the multiverse is a prediction, not an assumption. We don't reject black holes because we can't visit them. We don't reject the Big Bang because we can't rewind time. We accept them because they're consequences of well-tested theories. The multiverse is the same. Others worry about the philosophical implications. If every possibility happens, does anything matter? If there's a universe where you succeeded and one where you failed, does your choice matter? Some argue this leads to nihilism, but others counter that it makes your choices more meaningful. In your branch of the multiverse, your decisions determine which path you take. You can't access other branches. You're stuck in this one. So your life, your experiences, your consequences, they're real and matter deeply, even if other versions of you exist elsewhere. There's also the question of identity. If there are infinite copies of you, are you all the same person? Or are you distinct individuals who happen to be identical? Philosophers call this the problem of personal identity in a multiverse. The answer depends on what you think makes you, you. If it's your memories and experiences, then each version diverges the moment a difference occurs. If it's your physical structure, then identical copies are identical people. But you'll never meet them, so it's more theoretical than practical. And what about probability? In an infinite multiverse, everything that can happen does happen infinitely many times. So how do you calculate the likelihood of anything? This is called the measure problem. It's one of the biggest unsolved challenges in multiverse cosmology. If every event happens infinitely often, then naively, every event has infinite probability, which is meaningless. Physicists are working on it. Proposals include weighting universes by volume, by entropy, or by complexity. But there's no consensus yet. Despite the challenges, the multiverse is here to stay. It's not fringe science anymore. It's mainstream. Top universities have research programs studying it. Major physics journals publish papers on it. Nobel Prize winners defend it. Because whether we like it or not, our best theories point toward it. Quantum mechanics suggests many worlds. Cosmology suggests eternal inflation. Fine-tuning suggests anthropic selection. Mathematics suggests Tegmark's level 4. None of this is certain, but it's compelling, and it's getting harder to ignore. So, what does this mean for you? It means that right now, as you're reading this, countless versions of you are living out every possible variation of your life. Some better, some worse, some unimaginably different. You'll never meet them. You'll never know their stories. But they're real as you are. And in a strange way, that's comforting. Because it means that every path you didn't take, every choice you didn't make, every version of yourself you wonder about, they exist. Somewhere. In the infinite branching tree of reality. You're not alone. You're one among infinite siblings, scattered across the multiverse, each living their own unique existence.